Our next topic is we're going to be working on thermodynamics, which is the energetics of chemical reactions. Our first part, we're going to take a look at enthalpy of reaction, which is oftentimes known as the heat of a reaction. This is endo and exothermic processes. The two possible processes are we can have a chemical reaction where energy has to go into the reaction, and we also have chemical processes where energy is released as part of the chemical change that takes place in the reaction. Energy in processes are known as endothermic reactions. Energy coming out are known as exothermic processes. In an endothermic process, the products are going to end up at a higher energy state than the reactants. A graphical depiction, we would see chemicals A and B are reactants at a certain energy level, and then the products will be at a higher energy level, C plus D being at this particular energy level, indicating that there's been energy taken in as the reactants have changed to product. On the other hand, in an exothermic process, we'll see that our reactants have a particular energy level. The products will be at a lower state of energy, and the difference in energy as we go from reactant to product would be the quantity of energy that gets released to the surroundings as the chemical reaction takes place. The difference in the energy level between reactant and product on our diagram is known as the change in enthalpy of the reaction. So in both circumstances here, in this case for the change again between reactant and product, this will be known as the change in enthalpy of the reaction. Now to calculate our change in enthalpy of a reaction, change here means that we're going to compare the final conditions to the initial. In this case, final conditions in a chemical reaction are products, the initial conditions are the reactants. So to calculate our change in enthalpy for a chemical reaction, we'll take the enthalpy level of the products and subtract from it the enthalpy level of the reactants. As we can see in this example of an endothermic reaction, the enthalpy level of our products is going to be a larger number than our reactants. So in the case of an endothermic reaction, when we calculate the enthalpy of reaction, we're going to get a number that's going to be a positive number. However, in the exothermic reaction, one of the characteristics of exothermic reaction, we can see here that the products are at a lower enthalpy level than the reactants. If we take a smaller number and subtract from it a larger number, we're going to get something that is negative. So for an exothermic process, the delta H, or enthalpy of reaction, will be a negative number for exothermic processes. Some things that we'll see as we work with enthalpies of a reaction are symbols and terminology such as this symbol where we have delta HF with a degree sign. What this represents is something known as a standard enthalpy of formation. The degree sign here indicates that we're under standard conditions, which for enthalpy, standard conditions, it's roughly room temperature of 25 degrees Celsius, and the pressure conditions would be under 1 atmosphere pressure, would be considered standard conditions. The subscript F represents formation, indicating that this is the enthalpy that goes into the formation of some type of compound. Now, one key concept with standard enthalpies of formation is that all elements in their naturally occurring state at 25 degrees Celsius and 1 atmosphere pressure have a standard enthalpy formation of 0. All elements are assigned a value of 0, and then when a compound forms from the combination of elements, there's either a net gain in energy or net loss in energy relative to a baseline of 0 for the plane elements. There's also something known as standard enthalpy of formation reactions. A standard enthalpy of formation reaction is a reaction to specifically show the formation of a compound. The purpose of a standard enthalpy of formation of a reaction is to determine the energy content of a molecule or compound, and also to represent what elements go into forming a particular compound. One unique feature of an enthalpy of formation of reaction is that they're always balanced to form only 1 mole, if we look at our examples, of only one product. Because what we're trying to show is what's the enthalpy that goes into forming one specific compound. So in both examples here we have one product and it's balanced such that there's only 1 mole of that product being formed. A second feature is that in an enthalpy of formation reaction, the reactants are always elements in their natural form at 25 degrees Celsius and 1 atmosphere pressure. So if we look at this, all the reactants here in our examples are only elements in their naturally occurring elemental form. And then the reaction gets balanced, which means if necessary we use fractions to balance the equation so that we always end up with only 1 mole of one type of product. Another concept we'll be using in this unit is the law of conservation of energy. Essentially what the law of conservation of energy will tell us is that heat lost plus heat gained will add up to equal 0. Somewhat of a common sense law in that if something is losing heat, somehow, some way, somewhere, something else has to be gaining some heat. So however much heat is lost by something is equal to the amount of heat gained by another object. We can calculate the amount of heat lost or heat gained by using the equation mc delta T. Represents how much heat is gained or lost. In the equation, the m represents the mass of the object that's either gaining or losing the heat. C is a constant known as the specific heat, which is a unique constant to every different type of material or substance. And delta T is just the temperature final minus the temperature initial of the object in question. The one material that we'll need to know the specific heat for is water. Here's several values of specific heat for water. In English units, which is the same as pounds and inches, it's 1 calorie per gram degree Celsius. The metric is 4.18 joules per gram degree Celsius, or in kilojoules, 0.00418 kilojoules per gram degree Celsius. What it represents is, for example, 4.18 joules per gram degree Celsius would mean for water it takes 4.18 joules of energy to make 1 gram of water change by 1 degree Celsius. One of the things in the lab exercise we're going to be called upon to experimentally determine the enthalpy of a reaction. This will be referred to as our enthalpy of a reaction experimental. The experimental value is something we would calculate using data that was collected in the lab exercise. This would be a sample set of data. Our mass of water that we used in the experiment was 300 grams. We've measured the temperature initial and temperature final of the water for the process of dissolving a sample of ammonium nitrate. The mass of ammonium nitrate dissolved is 24 grams. This is enough information for us to calculate the enthalpy of reaction for dissolving ammonium nitrate solid into water. We can calculate the amount of energy lost by the water using mc delta T. Inserting our data, we have the mass of the water is 300 grams, specific heat is 0.00418 kilojoules per gram degree Celsius, and our temperature change was a negative 6.1 degrees Celsius. We can calculate the heat lost by the water. If we look at our unit for the specific heat, we can see the grams here will cancel, our degrees Celsius cancel. The only unit left uncancelled is kilojoules, which is our measure of energy. Calculating this, we find the heat lost by the water is a negative 7.65 kilojoules of energy. Now, using the law of conservation of energy that says heat lost plus heat gained equals 0, if we know that the water lost 7.65 kilojoules of energy, therefore we can say the heat gained by the ammonium nitrate solid dissolving would be a positive 7.65 kilojoules of energy. From our data, we have that 24 grams of ammonium nitrate dissolved. That amount of grams took 7.65 kilojoules of energy from the water for the process of dissolving. That's why the temperature of the water went down, because the water was losing energy to the ammonium nitrate dissolving. Typically, we want to get our enthalpy of reaction expressed in terms of how many kilojoules were absorbed or lost per mole. So we have to switch our grams of ammonium nitrate to moles of ammonium nitrate using a proportion. we find that 0.3 moles of ammonium nitrate dissolved, and in so doing, the ammonium nitrate gained 7.65 kilojoules. We'll now use another proportion to find out the heat per mole. Our proportion, we know that we have 7.65 kilojoules that were taken in by 0.30 moles of ammonium nitrate, so we can solve for how many kilojoules would have been taken in for 1 mole dissolving. Solving, we find that our experimental enthalpy of reaction comes out to a positive 25.5 kilojoules per mole. To get a known enthalpy of reaction, what we would do is look for standard enthalpy of formation values for our products and for our reactants. And if we take the enthalpy, a total enthalpy for our products, and subtract from it a total enthalpy of our reactants, that'll allow us to get a known value for our enthalpy of reaction. For example, let's say we wanted to find the known enthalpy of reaction for the combustion of propane. First, we write and balance our equation for the combustion of propane. The table we have here provides us with what are known as enthalpy of formation values, or the enthalpy content of all of our compounds we have in this reaction. We have our value for propane, oxygen, carbon dioxide, and also water. We're using water in the liquid state because the calculation will be done for the physical state that things are in under standard conditions, which is 25 degrees Celsius and 1 atmosphere pressure. Under those conditions, water exists in the liquid state. To get our known value, we're going to use our enthalpy content of our products and subtract from it the enthalpy content of our reactants. We'll also put it into a graphical picture to help visualize what's taking place. Our first step is to add together all of our product totals. Now in here, because there's a 3 in the balance equation for CO2, we'd multiply the value of CO2 by 3. Likewise, where there's a 4 for the water, we'd multiply the value of water by 4. Adding all of this together will give us an enthalpy value for our products. We do likewise for the reactants. We add up all the enthalpy values for all of our reactants, and here we'll notice oxygen has a value of 0 because oxygen is an element in its naturally occurring state. The value we get for our products is negative 3,110.7 kilojoules. The reactants is negative 104.7 kilojoules. These values would let us know the levels of enthalpy we're at in our graph. The products are at a level of negative 3,110. The reactants are at a higher level of energy, being only at negative 104.7 kilojoules. Our difference between where we start and where we finish is going to be our enthalpy of reaction when we take the products minus the reactants. Calculating our enthalpy of reaction, we get a negative 3,006 kilojoules per mole reaction. Mole reaction means this is the energy released per the balanced equation when the equation is in its balanced low whole number coefficient form. Also, by being a negative here, this tells us this particular reaction is exothermic, in that the energy was released to the surroundings as the reactants turn to product. The last component of our lab exercise is concerning Hess's Law, which has to do with additivity of heats or enthalpies of reaction. What Hess's Law tells us is two things are true when we consider Hess's Law. One, the enthalpy of reaction of an overall equation is the sum of the individual enthalpies of reaction of individual equations that may be combined. And the second thing is the value of the enthalpy of a reaction is the same whether it occurs in one step or one reaction, or if we add together several reactions to get a heat of reaction. This would be an application of Hess's Law. Let's say we're given two reactions. We have A plus B goes to D. We're given our enthalpy of reaction for that as positive 10 kilojoules. E plus F goes to 2D. And for that process, our enthalpy of reaction is negative 8 kilojoules. We want to try to combine these reactions to give us a new overall reaction of A plus B goes to 1/2 E plus 1/2 F. Here's what we can do. The A plus B goes to D reaction remains as is, because we want to have our A and B remain as reactants. However, our E and F that we have here need to end up as products and be only half as much. So the second reaction here, we're going to flip and write it backwards and chop it in half. By flipping it, that takes the sign of the original enthalpy of a reaction and changes it to a positive 8 kilojoules. And by dividing the reaction in half, the amount of energy we would get would also be cut in half. So we cut the enthalpy of a reaction in two. To now get the overall heat of enthalpy of reaction for the new process, we just have to add together the heats of reaction from the reactions that were combined to give us the overall. Combining the manipulated reactions, we have a positive 10 kilojoules for one, positive 4 kilojoules for the other. Adding them together will give us our new enthalpy of a reaction for the overall reaction of a positive 14 kilojoules.